All right, today we're going to start chapter 4, and a lot of what chapter 4 is using the derivative to analyze a function a bit more in depth than we have been doing. So that's where the extrema part's going to come in, and then we're going to use some of those ideas for optimization. And optimization is, think efficiency, but kind of in mathematical terms. So we're going to start with Extrema, and then we'll move into some optimization a little bit later on. But first thing we're going to start with are absolute and relative extrema. So if you take a look at this curve, now assume this is a closed domain. So assume the domain is closed. So what I mean by closed, just go back to your definition. It just means you include your endpoints. So if we take a look at this and say, okay, what are the largest and smallest values? So just taking a look at it, clearly this would be our largest peak, and this would be our lowest valley of these. So this is the smallest value. And then we have the largest value. So these are what we would refer to as our absolute maximum and minimum point, our absolute largest value and our absolutely smallest value. But there's also the idea of a relative largest and relative smallest. So you can think about it as maybe in a group of friends, you're the shortest, or in a group of friends, you're the tallest. But you expand that group out to be the whole school. Now, you may still be towards the top part, or you may still be towards the bottom part, but now you were only relatively the tallest. So let's take that idea here. So a relative minimum would technically be here, because what you want to do is think of the idea of, if I were to take a open interval, so like if I went from like here to here, this point's now the smallest point in that interval. Because, and I'll erase these in a second, let's say I take this interval, which includes the two purple points. This is the smallest point in that interval, and this is the largest point in that interval. But if I were to extend it to over here, the tallest point hasn't changed, but the smallest point has. And a similar idea, if I were to move, so let's call these 1, if I call these 2, now your shortest point is this blue dot, and your tallest point is the red dot. So relatively speaking, think about the parentheses as being like the group of friends, or how many people are you including in the group when you're discussing it. So then this would also be a maximum. This would be relative. This would be a relative min. And then another point here, this would also be a relative minimum. Because again, use the parentheses and just say, okay, if I were to make an interval, would this be the shortest point in the interval or the smallest point in the interval, or could it also be the largest? Now, the other thing is, remember I said assume the domain is closed. So that means the endpoints as well. This would be a relative maximum. And this endpoint as well would also be a relative maximum. So the endpoints can be relative maxes or mins, just depending on where they are in the function. Now the other thing to keep in mind, if you are the tallest person in the class, or sorry, if you're the tallest person in your friend group, and then you expand that out to be also you're the tallest person in the classroom, and then maybe you expand out and be, oh, you're now the tallest person in the school, you were not only the relatively tallest, but you were also the absolute tallest. So these points as well, this is also a relative max. And even your smallest point is also a relative minimum. So if you're absolutely the tallest, you're also relatively the tallest. But if you're only relatively tall, that does not imply that you are absolutely the tallest. So you have to keep the endpoints in mind. And you have to keep what's the largest value, what's the smallest value, absolutely. And so you can use everything to figure that out. But now, what if I took the picture away? And I said, what are the largest and smallest values on this interval? Well, things aren't quite as easy now. Because now you look at that and go, well, I don't have anything to work with. So this is where the derivative is going to come into play. Because remember, we talked about if it's the derivative 0, there's a possibility that that could be either a peak or a valley. So we can use that information and figure out, okay, where are the horizontal tangents? Because if there's a horizontal tangent, remember that means the derivative is equal to 0, which means it goes either from increasing to decreasing or decreasing to increasing, or the very odd occasions where it's increasing, stops, and then increases again, or the same thing for decreasing. So there's what our graph was. That was what we just dealt with. Now the question is, how do you actually find that? The other thing that would be very important is, where are there no tangents? Where is the derivative undefined? And remember, the undefined would be something like you divide by 0. Because it's a negative under the square root, while that is undefined, that's also not in the domain to begin with. So you do have to keep in mind of the original domain as you go along with these. And then, of course, the endpoints, because if you start with someone and maybe you're taking a survey of people, then the endpoints, in this case, they might change based on, again, who's the tallest, who's the shortest. But you do have a largest and smallest that you have to check at the very end, because take into account if it's a profit. I know I use profits a lot, but it works out really well. If you have a day 0, and then you have, let's say your projection only goes out for 90 days, then you have to check the maxes and the mins throughout that projection. But then you also need to check and see, okay, well, what was the profit at day 0, what was the profit at day 90. Because even though they may not be where the derivative is equal to 0, they are key points from there. So don't ignore the endpoints. So when you take the derivative, the nice thing is you've just taken the problem down from being what are all these points that I have to check to, all right, now I need to look at where does it equal 0, where is it undefined, and what are the values at the endpoints. So like for this function, if we took the derivative, we would get, so the first times the derivative of the second, which would be 4 cosine of 4x, plus the second times the derivative of the first, and then you would set that equal to 0. Now, fortunately for this one, it doesn't look like it's undefined at any point, because x is defined for all for all values. Cosine of 4x is defined for all values, and sine of 4x is also defined for all values. So 2 is not applicable here. So we would just say y prime is defined. Now we would say specifically for all x in 0.5 and 4.5. Now these are strictly less than, so I should make this brackets. So it needs to be technically really differentiable in the interval. And then we just need to see what is 0.5 times sine of 4 times 0.5 equals what, and also what is 4.5 times sine of 4 times 4.5. So these would be the steps that you would take in trying to determine everything. Now, for equation 1, that's going to be pretty tricky. You would probably have to set it equal, or you would probably have to solve for x, and then it would be turning into kind of where does 4x equal, I think that would turn into negative tangent of 4x. Yeah, because you would subtract over sine and then divide out cosine. So you get negative sine of 4x over cosine of 4x, which would be negative tangent of 4x. So it turns into where does 4x equal negative tangent of 4x, which I'm not going to make you do right now. So let's just go on to the next slide. So the definition of an absolute maximum and an absolute minimum. So let f be a function with a domain D. Just this could be closed, it could be open, it could be half closed and half open. But the definition for the absolute maximum is let f be a function with domain D, then it has an absolute max on the on the domain D at a point C if f of x is less than or equal to f of c for all x in D. What this means is f of c is larger than or equal to any value in your equation. So if you had something like this, let's say this was your cutoff for the domain. Let's say this was f of c, and then let's say that it was equal to this point, which we'll say is f of d. then that's okay. It's okay to have that value be the same. As long the key takeaway is that it is the largest value in the whole domain. It can occur multiple times, but there should be nothing that exceeds it. Absolute minimum is the same way, except it's the smallest value regardless. So this would be something like if you had a parabola that opened like this, that would be the smallest point. There would be no other points. But if you took something like this, and again, we're going to assume these are domain cutoffs. Notice for this one, the minimum point is actually the end point. So this is why we say don't just check where the derivative is 0, also check on the endpoints. Because I think for this first one that I drew, this would actually be the left endpoint would be your absolute minimum. But notice this one, the absolute maximum occurs twice, and that's okay. You just need to identify what's the absolute maximum and what's the absolute minimum. All right, the extreme value theorem. Every single part of this theorem is important. And I'm going to go through and underline all the things that I mean about that. If f is continuous on a closed interval, then f attains both an absolute maximum value, which we call capital M, and an absolute minimum value, which we call lowercase m, in the interval AB. So, take into account what that says. If a function's continuous on a closed domain, then it's going to have both an absolute maximum value and an absolute minimum value. And every single part of that preceding, everything that precedes the then is important. You can't have just one. You have to have that it's continuous, and you also have to have that the interval is closed. And figure 4.3 is in the book. So these points where the maximum and minimum occur, or where the maximum is achieved, are very important. Because, like I said, maybe it's profits, maybe it's a function that models the strain on an engine. So you need to know what's the maximum and what's the minimum output of this. So the fact that you have a closed interval is very important, because you are saying within this time frame, I definitely can say that it attains a max and a min as long as the function is continuous. So some examples. Now these are all going to be, so let's take a look at this first one. So this one's just kind of like a cubic function, and you can see that it's cut off at A and B. And so you have a maximum value here at x2, and then you have a minimum value here at x1. Now, notice here, this is in absolute values. If you say what is the smallest value it obtains, you do want to specify that it's like, this might be like -3, and this might be +4. If you say what's the absolute smallest, then you might be saying what's the smallest value it obtains, or it attains, but I don't really care what the sign is. So that's kind of the important distinction. So most of the time, though, you're going to want what's the smallest point here, and what's the largest point. It's there. Now here's one where, notice this function is strictly decreasing, whereas this function, it increased, then it decreased, and then it increased again. This one is strictly decreasing. And because the function's strictly decreasing on the closed interval, that means this endpoint is your max, your absolute max, and this endpoint is your absolute minimum. Notice if we went back to here, just to be consistent, this endpoint, this would technically be a relative max of the function, and this would be a relative min of the function. But we don't have that here. The second the second graph is only absolute max, absolute min, which means they're also relative max and relative mins as well, but we have none other than those two endpoints. So sometimes your only extrema are going to be on the endpoints just based on the nature of the function. Here's one where you have one of the maxes being attained on the interior, and you have the minimum being attained on the endpoint. So you can have a mix of the two where one of the endpoints is one of the valuable points for the absolute, and in the interior, one of those points ends up being where either an absolute max or an absolute min occurs. So that means your endpoint here, B, is a relative min. And notice the way that I label these. Relative min, notice this is kind of a little obvious for this one, but min, max, minimum, maximum to minimum. So notice it never goes maximum, because if that was the case, like if we did something like this, and you tried to say, oh, well, this is a maximum, and then this is another absolute, or this is a relative maximum, because if I do this, but then technically that point should be, so you don't have these sequential max and min. And here's the reverse kind of this function, where the minimum's on the interior and the maximum's on the end. And then our endpoint A is a relative maximum. So these are just some examples of how you'll see them presented. And the key thing about Theorem 1 is that it says the interval is closed and the function is continuous. It does not tell you where they are. That's up to you. So that's the kind of one of the cruxes and convenient yet inconvenient things about these existence theorems. They will tell you, hey, it's there. You can find it. And you go, cool, where is it? And it goes, I don't know. I just know it's there. And you just kind of have to glare at it for a second and go, okay, well, I'll go find it. And so then that's when you do the test for the endpoints. Where is the derivative equal to 0? And where's the where's the derivative undefined? So you have to keep those three things in mind. That all the theorem says, the extreme value theorem, is that if it's closed and if the interval is closed and the function's continuous on that closed interval, you get an absolute max and an absolute min. It tells you nothing about where they are. So is f prime equals 0 at extrema? Not always. just for example, notice these endpoints. The endpoints were never, or not that they were never, but they don't have a derivative equal to 0. You could have a case where the endpoint has a derivative equal to 0. Like maybe for this equation, maybe if you started it here at x1 and made the interval from x1 to b, yeah. But notice it really only applies to the derivative being 0, mainly applies to these functions being, or the interior of the functions. Most of the time, you don't have a case where the endpoints are shared with, or not necessarily that the endpoints aren't shared, but the endpoint typically isn't also a place where the derivative equals to 0. You just have to keep those ideas in mind. So I did kind of harp and say that you had to have that it was continuous on a closed interval. So if you say, well, what if, is that really necessary? And this is one quick example. So here's a function. Its domain is from 0 to 1, and it's closed. The difference, though, is you never get a largest value. Because notice this is defined on the closed interval from 0 and then the open interval to 1. So that means I can take a limit as x approaches 1 from the left, and I would get 1, but that's the limit. I don't ever get there. Because if you say, oh, well, the largest value is 0.9, I can go, no, it's not. It's 0.99. And somebody else can come along and go, no, it's 0.999. And you get this argument goes on forever. So, what do? You say, well, theorem 1 doesn't apply. Because the extreme value theorem, so you can say theorem 1 or the extreme value theorem, because this one said, or the extreme value theorem said I was guaranteed if it was continuous on a closed domain. This is on a closed domain, but it's not continuous, so I never get a largest value. So what if I say, what do I need to make the closed interval necessary? Well, let's take a similar function. Let's just say y equals x on 0 to 1. This is continuous, but we can have that same argument that we had up here about 0.9, 0.99. So I can have this argument, but now I can start a new argument and say the smallest one is 0.1. You can say, no, it's 0.01. And then somebody else comes along and says, no, it's 0.001. And then you have the same same argument, but you head towards 0 as opposed to heading towards 1. So both conditions are necessary. It has to be continuous, and it has to be on a closed interval. Notice, though, it didn't specify that it has to be differentiable. Remember, if a function is differentiable, it's continuous. But just because a function is continuous doesn't mean it's differentiable. So that's one nice thing you don't have to worry about. So let's see, are these graphs consistent with theorem 1? So they're all defined on 0, 4. So we have the closed interval. So all of them are going to have a closed interval, so that's pretty nice. So then if we look at the absolute extrema for this one, well, I have one there, and I have one there. The function was continuous, and this is one thing to point out. This was continuous, but not differentiable. But that's okay. The function didn't say it had to be differentiable. It just said it had to be continuous. So with that, we can say, so is it consistent with theorem 1? Yes. Let's take a look at this one. All right. I do have an absolute minimum down here, and it looks like I've got an absolute maximum about there. But it's not consistent. What's the reason? It's not continuous. So notice in this case, I got a maximum and an absolute max and an absolute min, but it wasn't consistent with theorem 1. To reiterate, that's because theorem 1 is purely an existence theorem. It does not say that you have to have both, or it doesn't say that if there isn't a continuous function on a closed interval, then you don't have these extrema. Notice it's not an if and only if. It just says if you meet these conditions, then you'll have an absolute max and an absolute min. It doesn't say if you don't meet them, then it doesn't happen. Now, there are cases where that does occur. Go back to the y equals x example. That one was inconsistent with theorem 1 and had neither a max nor a min. But this one, it's inconsistent with theorem 1, but it does have a maximum and a minimum. It just doesn't, theorem 1 just doesn't guarantee it on that function. Similar idea here. This is going to be defined, but again, it's not continuous. So it's not consistent. And this one has no absolute max or absolute min. And this one is also inconsistent because, once again, it's not continuous. It can be continuous but not differentiable, and it will still meet the requirements. But your requirements are very clear. Continuous on a closed interval. To guarantee. Just because it's not continuous and just because it's not a closed interval doesn't mean that you're not going to have an absolute max or an absolute min. You're just not guaranteed that. So keep in mind that theorem and what it says. It's purely about the existence of these solutions. It's not just about it's not about saying, I'll tell you where they are and I'll tell you if they're there or not. All it said, or actually that last part is what it is. I'll tell you if they're there or not, but I can only guarantee them. I can't say if it fails one of the conditions that it doesn't happen, because the second graph, the green one, is the key. It's kind of the key to what I mean by the theorem can only guarantee. Nothing about the theorem said that if it's not continuous, or if it's not on a closed interval, then it fails to have them. It just doesn't guarantee that it'll have them. but it can occur. So we're going to do a little bit more with the absolute max and the absolute min, but that'll be for the next lecture.